Now we're going to consider how the domain changes when we are working with complex rational functions. And in this case, when we are considering the domain changes, the complex rational expressions have a very similar property as to what we need to consider when we work with division for rational functions, where we kind of have to think about all the little denominators that were involved to start with, but also we want to make sure whatever we divide by is not equal to 0. So these are the considerations we have to take into our process when we are calculating this domain restriction. So if we look at part 8, we have this function, and right away we will see their denominator in the denominator and denominator in the numerator. So right away, the first thing you would want to denote is d doesn't equal to 0, because that's our denominator. We want to make sure that these denominators themselves are not equal to 0. But moreover, we want to make sure this entire big denominator is not equal to 0. So the entire denominator for the complex fraction is d over 1 minus d. We want to make sure that doesn't equal to 0 either. And in order to work with this part, we can really think about what is going on in this whole process. So one way to solve this type of equation is, or inequality, is we can multiply d on both sides of the equation or inequality, because we know in this case, in order for d to be in the denominator, d cannot be 0. So if I multiply d on both sides, then I would be able to cancel out the denominator over here. Let me just change to a different color just so our color coding is a little bit easier. So I don't want this to be equal to 0. And I can multiply everything by d. And once I do this, I will have d squared minus 1, because I need to distribute the d. And that's not equal to 0, because 0 times d will be equal to 0. And once we get to this form, you can use either the factoring process or the square root property to solve this. And once we get that, we can see d plus 1, d minus 1 doesn't equal to 0. So d doesn't equal to plus or minus 1. And now that we have considered all the little denominator components we have to look at, we know the overall restriction for the domain is d doesn't equal to 0, 1, or negative 1 over here. And once we have this, we can start thinking about how we can simplify this. And to simplify complex fractions, we can always start using the least common denominator, no matter which method you choose to use. And here, if we look at the least common denominator, because the numerators on top and bottom are both d, we would know that the least common denominator is just equal to d over here. So that means I'm going to multiply everything by d. And just as I multiply d on both sides, I'm making this condition that d is not equal to 0, because otherwise it wouldn't be a valid operation. If I multiply the same number on both sides, I need to make sure that neither number is equal to 0 over here. So I'm already using the domain restriction that d doesn't equal to 0. And once I distribute d to every term, I would have the result being d plus 1. So I'm just distributing d to everything. And then on the denominator, I would have d squared minus 1, just as we did already in the domain calculation. So on top it's d plus 1, it's linear, we can't factor it anymore. On the denominator, we factored it when we calculate the domain. It's d plus 1, d minus 1, it's a difference of squares. And once we do so, we can see d plus 1 is in common, and we can cancel that out. In order to cancel that out, we require d plus 1 to not be 0. In other words, d doesn't equal to negative 1. And now if we want to go further, we can see on top we are just left with a factor of 1. On the bottom, we are left with d minus 1. So for the final domain restriction, we want to make sure it's d such that d doesn't equal to 1. Comparing the starting domain restriction to the ending expression domain restriction, we had 0 and we also had -1 to start with. Again, these were used in the middle process for cancellation, but they were not part of the domain restriction if we only look at the final expression. Moving on to part B, we can do the same thing. Look at the domains over here. We would get t doesn't equal to 0 because t is a denominator on top and bottom. We also want to make sure t squared doesn't equal to 0, which actually gave us the same result, that t is not equal to 0. They are given the same answer. And then we also want to make sure the overall denominator, 3 plus 1 over t, doesn't equal to 0 over here. And to solve that, you can multiply t on both sides. Again, just as we did before, we can multiply t on both sides because we are assuming t doesn't equal to 0, because t is now in the denominator. And once we do so, we would have 3t plus 1, so I'm distributing t, that's not equal to 0. And therefore t doesn't equal to -1 over 3 if we solve that linear equation. So altogether, we see the domain restriction is t such that t doesn't equal to 0 and t doesn't equal to -1/3. So with these, we can go in and work with the operation. So the least common denominator in this case, if we look at all the denominators we have at t, t squared, and t, so the least common denominator would be t squared in this case. And that means we can multiply everything by t squared. Everything be every single term. So now we get 9 over t times t squared, which would be 9t, because one of the t's cancel out, plus 3 over t squared times t squared, would just be 3. Then on the denominator, we have 3t squared plus t, because again, 1 over t times t squared has one factor of t cancelled out. So once we get to this form, we can look at the factoring. On top, we have a GC of 3 to factor out, which gives us the 3t plus 1. On the bottom, we have a GC of t, which gives us 3t plus 1 as well. And once we do so, we can see that we have a common factor of 3t plus 1 we can cancel out. And in order to cancel it out, rely on the fact that t doesn't equal to -1/3, which was in our domain restriction, and we're using that. And we have a result of 3 over t, so if we only look at the final result, we see the domain is t such that t doesn't equal to 0 over here. So the domain change for the beginning to the end is that -1/3, which got used when we were doing the cancellation. Moving on to part C, and this is part C, not part A, by the way. And in this case, when we look at this part over here, this is part C, and we can look at the denominators again individually. So we want to make sure x plus 3 doesn't equal to 0, which gives us x doesn't equal to -3. We have x minus 1 doesn't equal to 0, giving us x doesn't equal to 1. X plus 2 doesn't equal to 0, which gives us x doesn't equal to -2. Right? And now if we want to make sure the entire denominator doesn't equal to 0, that means we want to make sure that 3 over x plus 2 plus 1 over x plus 3 doesn't equal to 0 over here. And in this case, you can see we have two rational expressions. In order to simplify that, we need the least common denominator over here. So this is almost like a mini problem over here. The least common denominator for these two would actually just be the product of 2, because these two denominators don't share anything in common. So if I multiply everything by the product, I'm just going to go ahead and distribute that LCD to every single term on the left and on the right. And on the left, we can have a little bit cancellation. We would just be left with 3 times x plus 3 plus 1 times x plus 2. That's not equal to 0, because 0 times anything is 0. And once we get to this form, we actually have a linear inequality. So we get 3x plus 9 plus x plus 2 doesn't equal to 0. In other words, 4x plus 11 doesn't equal to 0, or x doesn't equal to negative 11 over 4. So putting everything together, our domain is x such that x doesn't equal to negative 3, 1, negative 2, or negative 11 over 4. So 4 restrictions we have to consider. And altogether, we would have this entire expression to work with. So to simplify that, we again need the least common denominator. In this case, we can see we only have two denominators that are the same, and all the other different denominators are not multiples of each other. So that leaves our least common denominator being the product of everything. So it's just all three denominators that are distinct altogether. So that means every time I see a term, I'm going to multiply that by the least common denominator. So I'm going to need a bit more room over here. And as a result, for the first term to be multiplied by the LCD, you will see x plus 3 getting cancelled out. So I'm left with 5, which was originally there, x minus 1, and x plus 2, because that x plus 3 got cancelled out. Minus, for the second term, x minus 1 got cancelled out, so I'm left with 1 times x plus 3 times x plus 2. You don't have to write the multiply by 1 because it doesn't change the result. And this is all over. Now in the denominator, that 3 stays, and then x plus 2 cancels out, so I'm left with x plus 3 and x minus 1. Lastly, plus 1, 1 stays, multiply by anything other than x plus 3, because x plus 3 get cancelled out. So that should be what we have. We don't have a complex fraction form anymore if you multiply the LCD properly. And yet we have this expression that's not the easiest to work with. So in order for us to go further, we actually have to simplify the numerator and denominator separately before we can do any factoring or simplification. I know it's tempting to look at what they all have in common, but remember they have things in common right now precisely because we multiplied them all by the LCD. So now we actually have to go through some algebra, the FOIL process, all these. So for x minus 1, x plus 2, feel free to pause the video to go through the process yourself, but I'm just going to do this in one step. And we would have x squared plus x minus 2 here in the FOIL process. And then for the second, when we do the FOIL process, we get x squared plus 5x plus 6. On the denominator, we have 3 times x squared plus 2x minus 3 plus x squared plus x minus 2 over here. Alright, so after doing all the FOIL process, I can go ahead and distribute all the things to get rid of all the parentheses. So that's my goal next. So 5x squared plus 5x minus 10 minus x squared minus 5x minus 6 all over 3x squared plus 6x minus 9 plus x squared plus x minus 2. No more parentheses, so we can combine like terms with no issue. On top, I would have 4x squared, 5x and 5x cancel each other out. And then I have minus 10 minus 6, which would be minus 16. And then we would have on the bottom 4x squared plus 7x minus 11 over here. Alright, we have some interesting numbers to work with. On top, we notice there's a GCF right away, so that 4 can be factored out, and we're left with x squared minus 16 over here, which if you can, x squared minus 4, excuse me, because I factored out the 4. And if you recognize that right away, you can go ahead and factor that out to be a difference of squares, or you can leave it to the next step. Now on the denominator, we can look at that AC method possibility, and we get a times c is equal to 4 times negative 11 in the denominator, which is negative 44, and basically that tells me the product is negative 44. And the sum needs to be positive 7, and if we think about the factors of negative 44, we should have the two numbers being 11 and negative 4. So that's what I'm going to do. I'm going to rewrite the middle term to be 4x squared minus 4x plus 11x minus 11. So we can do factor by grouping over here. Now on top, we have 4 times x plus 2, x minus 2. On the bottom, to do factor by grouping, I would get 4x as GCF first, x minus 1, plus 11 times x minus 1, and I get 4 times x plus 2, x minus 2, all over 4x plus 11 times x minus 1 over here. Alright, so everything's fully factored, and this is the first time we can actually check whether there's any cancellation. And turns out, sadly, there is no cancellation. We completed the operation, we simplified the expression, so we're all good, but we don't have any cancellation. Nonetheless, we can still consider the domain restriction at this point. So we want to make sure the denominators are not equal to 0. So we want to make sure 4x plus 1 is not equal to 0, which will give us x doesn't equal to negative 11 over 4. If you wonder how I did this so quickly, just look to the left. That's where we did all the calculation earlier. And we also want to make sure x doesn't equal to 1 over here. So you can see, even though we didn't have any type of cancellation, in order for us to multiply the least common denominator, we're already relying on a lot of the fact that if I want to have that least common denominator being multiplied to both sides, I'm requiring essentially this doesn't equal to 0, this doesn't equal to 0, this doesn't equal to 0, in order for the product to be not equal to 0. So that's where all the consideration for negative 3, 1, and negative 2 come into play. And that's why in the final result, even though we only have 2 factors, the other restrictions were still being incorporated. So we have that difference of the negative 3 and negative 2 being the domain restriction in the original expression. Lastly, for part D, if we want to look at this expression, we have the same considerations as before, that any existing numerator and denominator doesn't equal to 0, so x plus 1 doesn't equal to 0, and x minus 1 doesn't equal to 0. These are done right away, and then we also want to make sure the entire denominator is not equal to 0. And with this, I need the least common denominator, so the least common denominator here, again, will be the product of the two, because they don't share any factor. So I'm just going to go ahead and multiply. X minus 1 cancel out in the first term, x plus 1 cancel out in the second term. All together, I'm left with 5 times x plus 1 and 3 times minus 3 times x minus 1. Doesn't equal to 0. Again, this turns linear, which becomes 5x plus 5 minus 3x plus 3 doesn't equal to 0. In other words, 2x plus 8 doesn't equal to 0. X doesn't equal to negative 4. So altogether, the domain is x such that x doesn't equal to 0 and x doesn't equal to negative 4. This isn't as involved because we have fewer distinct denominators. And with this in mind, we can start working with the complex fraction. So we see that x plus 1 and x minus 1 are all the different denominators we have existing. So least common denominator would just be the product of the two, which is identical to what we did on the side to find the domain. And I'm going to draw a line just to divide this up a little. And now if we want to multiply everything by x plus 1, x minus 1, so I need a boundary here. If I do so, we can get that for the first term, x plus 1 get cancelled out on top and bottom, so I have 3 times x minus 1. For the second term, we have x minus 1 cancel out, so I'm left with 2 times x plus 1. Similarly on the bottom, I have 5 times x plus 1 minus 3 times x minus 1 altogether. And then we can go ahead and distribute things. We actually don't have any quadratic terms over here just because we only have a product of 2 factors and everything had a denominator, so there was some cancellation. Everything ended up being linear. So on top, 3x minus 3 plus 2x plus 2. On the bottom, we already calculated on the side. We actually should always have 2x plus 8 as at the end. If you want, you can do it again just to check that you did everything properly. And now in this case, we would have 5x minus 1 on top and 2x plus 8 on the bottom. Because everything's linear, the most we can do is a GCF on the denominator. And this tells us the domain restriction I would have as a result is x such that x doesn't equal to negative 4. And again, I technically use the domain restriction, which I noticed that I forgot to write the 1 and negative 1 in the domain restriction completely. So remember, we had that 1 and negative 1 we found through the denominators, which I completely forgot. Something that to be very careful with. And once we have this, if we look at the current restriction compared to the original restriction, we see that we don't have a factor of x anymore, so we really didn't have the domain restriction of, actually we didn't have a domain restriction of 0. I don't know why I wrote it, but the domain restriction to start with was 1, negative 1, and negative 4, and now we're left with negative 4. 1 and negative 1 were the differences which we had to use when we looked at the LCD. We want this to be non-zero, we want this to be non-zero, so that's where they got incorporated, even though there was technically no direct cancellation in the process.